Okay, so let's continue our discussion related to this particular course, Introduction to Electronics. We've been discussing digital circuit design, and in this particular lecture, we'll look at or we'll lay the foundation for combinational circuit design. And in the last lecture, towards the end, we had seen that if we have a truth table meaning a description of a function, a Boolean function, y, in terms of the input variables x1, x2, x3. And so this Boolean function, or we can express it either in a sum of product forms. Each term is a product term, and then we have sum of all these product terms here. And so we focus on the value on those terms for which the value of y is 1. And then we add up all these particular terms to obtain the Boolean expression here. So this is called the sum of products form. And there's a complementary representation where we focus on all the zeros, all the terms for which the y takes a value 0, and then we represent it in the form of what we call as a product of sum approach here. So if note that if x1, x2, x3 is y is 0 for that, then we represent this as x1 plus x2 plus x3, and that the whole thing is the product of. So each one is a sum term here, and there's another name for it. So each term is called each one of this is called a min term, and each one of these is called a max term here. So these are some terminologies that are commonly used, and this is called the sum of product representation, and this is called the product of sum representation here. All right, so what we need to do is we need to take these Boolean expressions and we need to implement it, and we implement it using gates. And an example of a gate, an elementary gate, is a AND gate. So AND gate, so if you have two inputs x1 and x2, so we represent the AND operation with a dot here, and we represent it with a symbol which is shown over here. Okay, and so the reason why we call it as a gate is, you can think of, let's say if this is an AND gate, if I make one input 0, then y will be 0. So the gate is closed. Y is independent of x1. On the other hand, if I make now y equal to 1, then this x2, the other input is 1, then x1 passes through this particular AND gate and y equal to x1 here. So the gate is open, and a value of x2 equal to 0 closes the gate. A value of x2 equal to 1 opens the gate and allows y to depend on the value of x1. All right, so so this is an AND gate, so it performs an AND operation. We've already seen what an AND operation means. So y equal to 1 when both x1 and x2 take values of 1 here. And then the OR operation is here. So OR gate is represented by this particular symbol here. And then, of course, this is the simplest gate that we can think of, which is a NOT gate, which is y is complement of the input here. We represent it by this particular symbol here. All right, so let's look at some more elementary gates. Then we have NAND gate, which is x1.x2 bar here. So it's basically, you can think of it as an AND gate followed by a NOT gate here. We'll also use the word inverter. A NOT gate is nothing but inverts the input. If x is 0, then y is 1, and so on and so forth here. So NAND gate is an AND gate followed by an inverter here. But it doesn't mean that when we actually use a circuit to realize it, this is how a NAND gate is built. Conceptually, one can think of NAND gate as AND gate followed by an inverter. All right, so this is the symbol that we use. This inverter part here, or the NOT gate part here, this bubble here comes over here to indicate that this is a NAND gate here. NOR gate similarly is OR gate followed by a NOT gate here, and so its symbol is, it is x1 plus x2 whole bar here, and so its symbol is same as OR gate followed by a bubble here. So that indicates, so note that bubble sort of denotes the NOT gate here. So it carries out an inversion operation here. So that's NOR gate here. Then there are gates, other gates also, for example, XOR gate here. So these are all 2 input gates that we've been considering. So x1 OR with x2 here. So that's the definition of XOR gate here. So x1 x2 bar plus x1 bar plus x2. So we've seen that from a truth table we can go to a Boolean expression. From a Boolean expression we can go to a truth table. So the inputs are x1 and x2. So we draw x1 and x2. The output is y here. And then what we do is we x1 and x2 take the value 0, 0, 0, 1, 1, 0, 1, 1. And for each one of them, we can substitute it here and get the value of y that is there here. So we put 0, 0 here. So this is 0. So obviously the first term goes 0 here. And the second term, well, x2 is 0. So the second term also goes 0. So y equal to 0 here. And similarly, we can see that y is equal to 1 when only one variable takes a value 1. If both variables are 0 or if both variables are 1, then the output y is equal to 0 here. So that's an XOR gate here. And we represent it. So if you're looking for how do I implement an XOR gate, well, if you have an AND gate and an OR gate, you can implement an XOR gate in this manner here. So x1 dot x2 bar. So you implement this using this particular term, using this gate here, AND gate here. x1 bar x2, you implement it with this particular AND gate, and then you have to combine the two results here. So you use a OR gate here. So we represent it in the form of an XOR gate. This is the symbol that we use. And similarly, we have an XNOR gate here. So XNOR gate is x1 dot x2 plus x1 bar x2 bar here. So y is 1 if both variables are either 0 or 1 here. Okay. So complementary form of this one here. This one is 1 when only one variable is 1. If and only one variable is 1. And in this case, both variables have to be either 0 or both variables have to be 1 here. So that's an XNOR gate here. So of course, we can build gates with more inputs here. So this, for example, we can build an AND gate with 3 inputs and 4 inputs. So AND gate with multiple inputs as shown over here. Similarly, you can build an OR gate with multiple inputs. So that's also possible. And XOR gate also you can build. For example, this is an XOR gate with 3 inputs here. And in this case, y equal to 1 if odd number of inputs is 1, which means if only one input is 1, or if all 3 inputs are 1 here. So you can check from the expression here. When all 3 inputs are 1, then y is 1. And in other case, only when one input is 1 here. The others are 0. Okay, in this case, x1 is 1, in this case, x2 is 1, and in this case, x3 is 1. So only when odd number of input is 1, then you get the XOR gate here. So we have to implement the Boolean expression using gates. So in digital design, what we are typically doing is that there's a circuit that we want to design which performs a particular function. For example, let's say we want to design a circuit which adds up which we call as a full adder, which means it adds up 3 bits of numbers here, x, y, z. Each one is a 1-bit number here, and you add it up and you create a sum bit and you have a carry bit here. Okay, so we'll not go into the details right now of how we write, but let's say by looking at, for example, you can create a truth table of s versus x, y, z. And similarly, carry versus XYZ here. We know how to carry out a 3-bit addition. And for example, if x is 0, y is 0, and z is 0, s is obviously 0, and carry is 0. On the other hand, if x is 1 and y equal to 1, and let's say z equal to 0, so then the sum is equal to 0 and carry is 1. Okay. Anyway, so we can create a truth table, and from the truth table we can then obtain the Boolean expression. We've already seen how to go from a truth table to a Boolean expression. So let's say we obtain these 2 Boolean expressions here. Now each one of these terms that you see here, we have seen that we can use a gate to realize it. For example, x bar, y bar, z bar. So we can realize using an AND gate and using an inverter like this here, using a NOT gate here. So we create x bar here, y bar here, z here, feed it into a 3-input or AND gate here, because each term consists of 3 inputs here. So 3-input AND gate here. So we create all these terms that you see here. We use a gate to create all these terms So X bar, Y bar, Z, and all these. So there are 4 terms, and so we use 4 AND gates to create it. And sometimes the input is fed directly, sometimes it's fed after a inversion. So that's why we require all these NOT gates here at certain places here. So you create all these terms here, and then all these terms have to be connected together through the OR operation. So we feed it into an OR gate here. All right, so that's a simple, straightforward implementation of this part here, S here. And similarly, the C part here, the carry part here could be very easily implemented here. Okay, so now the next step is, so fine, we realize that given a truth table, so you want a design circuit for performing some functions. So from the nature of the function that you want to perform, you get a truth table. From the truth table, you get the Boolean expressions. From the Boolean expression, you get the gate level implementation here. But now this is only a symbol. This is only a symbol of an AND gate. This is only a symbol of an OR gate here. The gates itself, we have to implement using transistors. All right, so we'll do a slightly abstract implementation and using switches, and realize that MOSFET acts as a switch. We have seen earlier that if you apply a gate voltage larger than the threshold voltage, then the current starts flowing through the MOSFET. There's an inversion layer, and the MOSFET turns on. If you apply a gate voltage which is much less than the threshold voltage here, then the MOSFET is practically off. The current through it is very, very small here. So basically, a MOSFET can be looked upon as a voltage controlled switch. By applying sufficient voltage, you can switch the MOSFET on. And when the MOSFET is on, the resistance through it is a small resistance. Or if you don't apply sufficient voltage, then the MOSFET is off. So let's say we have what we are calling it as a voltage control switch, right? So if you give an input X, and so switch is closed if X is high, and switch is open if X is low. So this is like our N-channel MOSFET here. You can think of X. Right now we are talking about X taking logical values 0 and 1, but low when voltage is low, that corresponds to logical 0, and when voltage is high, that corresponds to logical 1 here. All right, so let's say we have a switch like this here. If voltage is low, which means if I apply, let's say 0 volt, so there's no inversion layer in the MOSFET, the MOSFET is not conducting, the switch is open. If I apply a voltage which is higher than the threshold voltage, MOSFET is conducting and the switch is closed. Okay, so that's the nature of a switch here. And let's say we have another switch which is complementary to this. So this we just explained that this is like the behavior of an N-type MOSFET. We can also build a P-type MOSFET in which the source and the drain are P plus and the body is N, and that behaves in a complementary manner here. So in this case, let's call this switch SP, denoting that it corresponds to a P-type MOSFET here. So switch is closed if voltage corresponding to X is low. So when X is low, the switch is closed. And when X is high, the switch is actually open. So it's just complementary to that here. So N and P behave in this complementary manner here. So let's say we have these switches. We'll not go into the details. We'll not note that these switches could be represented by other kinds of transistors also. So we are doing a more general representation, saying that suppose we have these switches, a SN switch here, which closes when the input is voltage is high, and an SP switch here, which closes when the input is low. All right, so let's say we have this switch here. Okay, and so you could represent it like this also. Switch is closed if voltage X is high, switch is open if here, right? Okay, so suppose we create a circuit like this here. So we have these two voltage control switches here, and we take the SN switch here and we connect it here to ground, and we take an SP switch here and we connect it here. All right, so and we connect it to the voltage here, battery here, VDD equal to 5. So note that when we draw a bar like this, VDD equal to 5, what we mean is that this particular node is connected via battery of VDD to the ground here. Okay, so that's how the circuit gets completed here. Okay, all right, so what happens here? How will this circuit behave here? If X is low, then we know that if X is low, let's look at the property of the two switches, SN and SP. If X is low, SN is going to be open and this is going to be closed. So if this is closed and this is open, so this is open circuit, so output is going to be basically equal to 5 volts, which is high. So when X is low, output is high here. Okay, so low voltage we'll associate with the logic value 0, and high we will associate with 1. So when you apply a 0, you get a 1. Okay, and so this is like a NOT gate that we were talking about. Okay, and you can also think of, for example, you can go ahead and put a 1 here, and then what will happen is if it's 1 here, then this switch will be closed and this will be open, and then this particular output Y is connected to ground, so it is low, right? So it acts like a NOT gate. So we can build other gates also. All right, so let's see this behavior. X1.x2 bar NAND gate. So we can build a NAND gate because it is X1.x2, so we connect two of the switches in series here. So when you want to perform, X1.x2 is an AND operation, so we connect them in series here. And then the other network, if these two are in series, then these two become in parallel. So it's a complementary form of a circuit here. So let's see whether it performs a NAND operation or not. So we can check. So if X1 and X2 both are low, so X1 is low and X2 is low, both these switches are open. And if X1 is low and X2 is low, both these switches are closed, and therefore output is high. So that checks out. Similarly, you can see that both these switches have to be closed, then only the output will be connected to Y here, right? So only when X1 is high and X2 is high, when X1 is high and X2 is high, then Y is connected to ground and it is low. And when X1 is high and X2 is high, both the switches are open. So this part of the circuit is open here. So note that, you can think of it as a upper part of the circuit and a lower part of the circuit. We often call it as a pull-up network and we call it as a pull-down network. So either the pull-up network will be active in the sense that Y will be connected through one of those SP switches to VDD, or the pull-down network will be active. Y will be connected to ground through the SN type of switches here. So we can see that this circuit acts like a NAND gate here. So if we have these switches like SP and SN switches, which we said are like N-channel, this is like an N-channel MOSFET and this is like a P-channel MOSFET. So I could very easily replace this by a P-channel MOSFET here, a P-channel MOSFET here, and an N-channel MOSFET here, and an N-channel MOSFET here, and we'll get a NAND gate. So that's how you end up implementing NAND gate using transistors. So NOR gate, well, you can see that if I take these two SN switches, connect them in parallel. So because it's a plus operation, so plus meaning that one of these switches has to be on in order to connect Y to the ground here. So you connect them in parallel, and if they are in parallel, then the corresponding network here is in series here. So you can verify that only when both X1 is 0 and X2 is 0. If both of them are 0, then both these switches are off, Y is disconnected from 0. And when both X1 is 0 and X2 is 0, both these switches are on and Y is connected to VDD here. So it's only when X1 is 0 and X2 is 0, then only you get Y equal to high. Otherwise, for all other cases, you get Y equal to low here. So that behaves like a NOR operation here. And so like that, we can build, these are, remember that we've shown you how to build a NOT gate, how to build a NAND gate, and how to build a NOR gate here. And both NAND gate and NOR gates are universal gates in the sense that if I give you a NOR gate, using that NOR gate, you can build any other gates. You can implement any Boolean expression using a NOR gate because the Boolean expressions are built using 3 elementary operations. The inversion operation, the NOT operation, the AND operation, and the OR operation. So if you're looking at, if I give you a NOR gate, how do you create a OR gate? Well, before that, how do you create a NOT gate? So given a 2-input NOR gate, how do you create a NOT gate? Well, if you take X1 and X2 and short it, and X1 and X2 and short it, so you have one input, okay? And you will see that Y is nothing but X inversion of X here. So if you short x1 and x2, x1 and x2 here, it becomes a NOT gate. And it's already a NOR gate. So if you take a NOR gate, and if I take an output and connect it to a inverter here, or a NOT gate here, the whole thing becomes an OR gate. And similarly, think about it, that given an OR gate, how can you implement a AND gate? So if you can do an AND operation, if you can do an OR operation, and you can do a NOT operation, inversion operation, using any particular gate, that gate becomes a universal gate. Because with that, you can do anything. You can implement any Boolean expression, any truth table. So the typical simplified design overview is that if you're given a particular function that you want to implement, let's say a full adder function. So the first thing is that from the nature of the function that you want to implement, so you get a truth table. So these are the outputs and these are the inputs. So before you can implement something, you need to know what is the output versus input relationship you're looking for. And it could be an adder, it could be subtractor, it could be a multiplier, it could be anything here. And from the nature of the function that you want to implement, you know what the outputs are supposed to be, what the inputs are, and you also know the relationship between the input and output. And that relationship is captured in the form of a truth table here. And truth table is nothing but, you start with the inputs taking all possible values. So ABC, all possible values of the inputs are starting from 0, 0, 0 to 1, 1, 1. So this is an exhaustive list of all possible values that the inputs can take. And then you write down what value will the output take for each one of those combinations of inputs. So that's a truth table. Once you have a truth table, we know how to go take a truth table and get an expression here. For example, this is in the sum of product form of expression, where we focus on all the terms for which the output is 1 here. So we look at all the ones here, and all these terms then are represented by terms symbolically here. So once we have a Boolean expression, we can implement it in the form of gates like this here. So we have these elementary gates and NOT and OR. We could have also note that NAND gate is also an elementary gate. So we could have also directly implemented this one in terms of a NAND network completely using, we said NAND, NOR is a universal gate, NAND is also a universal gate. So the whole thing could be implemented entirely using a NAND gate here. This whole thing can be implemented using NAND gate or a NOR gate. So anyway, we have a network of gates which will implement the Boolean expressions. And then each one of these gates we have seen, for example, if it's a AND gate here, so AND gate is built by, this is, we just recognize that this is a NAND gate, and NAND gate followed by an inverter or a NOT gate, so that becomes an AND gate here. Right, so each one of these things can be implemented using the switches that we talked about. And we also realize each one of those switches is nothing but a MOSFET. So we get a transistor circuit. So you can see that you could transform each one of these gates into a transistor circuit like this, and you'll get a transistor circuit, a full transistor circuit, which will implement, perform the function of a full adder. So if you give 3 bits, it will generate a sum bit and a carry bit here. All right, so we realize that there are several important steps. Whenever you want to design something, you want to design it in an efficient manner here. And we also realize that, fine, we are given the block that we want to implement, so we have a truth table, and we get a Boolean expression. And then we implement it using gates, and then the gates is implemented as transistors. So we will see that going from a truth table to a Boolean expression. Now, realize that the final circuit that you get depends on how complicated is the Boolean expression here. So in this case, for example, we note that the sum, the expression is more complicated than the carry expression here. How is it more complicated? Well, what do we mean by more complicated? More complicated in terms of implementation, right? So for example, each term has 3 inputs here. Each term has 3 inputs here, X, Y, Z. We call them also literals. So this term has 3 literals in it. This term also has 3 literals in it. And each term is what we call as a minterm. This is a minterm, this is a minterm, and all that. Okay, so we'll come to that terminology. So This expression we can see here, this has 3 terms in it, while this has only 2 terms in it. So that's this term is simpler than this particular term. How is it simple? Well, you can see here a term like this requires a 2-input AND gate, while a term like this here requires a 3-input AND gate. So that's how this expression is simpler. Not only that, this has 4 terms in it, and therefore it requires 4 gates here. And then it requires a more complicated OR gate also. It requires an OR gate with 4 inputs. Realize that an OR gate with 4 inputs is more complicated than an OR gate with 3 inputs. So we can see that this is a complicated expression. This is a simpler expression. Therefore, the simpler expression results in simpler implementation. The more complicated expression requires a more complicated implementation. Now, more complicated implementation basically means that I will require more number of transistors to implement. And therefore, the circuit ends up taking more area. Area in the terms of, realize that all these transistors are actually built on a piece of silicon. All the transistors, we talked about monolithic implementation. So all the transistors, all the interconnections, everything is done on silicon itself. And the larger the area of silicon that is used for making a circuit, the more expensive the circuit becomes. Okay. And so the complexity of a circuit is tied to the complexity of the expression here. And we will see that this truth table to a Boolean expression, this final Boolean expression is not the optimized Boolean expression. Often what you can do is you can simplify the Boolean expression. And if you simplify it, simplify in the sense that, by combining certain terms and using those postulates and theorems that we talked about, we can obtain a simpler expression for S perhaps. And the simpler expression, the simple expression also corresponds to the same truth table. So we don't violate the truth table, but the expression is simple and therefore it will result in a simpler implementation. So an important part of design of digital circuit is trying to obtain a simplified Boolean expression which captures the truth table that we have here so that the implementation is simple. All right, so our focus then is on Boolean expression. And so we've been saying that, okay, so we have, let's say a truth table like this, and we can capture it in a Boolean expression in this particular form. So we'll introduce some terms, because when you read literature and you read books on this digital design, there are certain terms that are used here. We'll not go too much into details of that. So when you have 2 inputs, X and Y, the various terms that can be are 0, 0, 0, 1, 1, 0, 1, 1, 1 here. So when you have 0, 0, well, symbolically you can represent it as X bar, Y bar. And we call this, each one of these terms is called minterm. So we call it M0, the 0th minterm, because the net value is 0. 0, 1 is represented as, 0 is represented as X bar, 1 is represented as Y. So we call it 1. Why? Because the 0, 1 represents a number 1. In binary form. 1, 0 represents a number 2 and 1, 1 represents a number 3 here. So each one of this is called a minterm, and 1, 1 is called XY and M3 here. So we can also write the function F1, instead of writing it like X bar Y and XY bar, we could also say F1 has a minterm 1 and a minterm 2 here, M1 plus M2. And then we can also, because it's a sum, we can also use a shorthand notation that F1 is sum of minterms 1 and 2. So we can describe a function in a much more compact and simple manner by describing what all minterms does that particular function contain. Meaning, what are the minterms for which the function's value is 1 here. Okay, so in this case, the function's value is 1 for a minterm 1 here. 1 is 0, 1, and for a minterm 2 here, which is 1, 0 here. Okay. Well, so in this notation, what does the function 0, 2, 3 denote? Well, what it means is that function F2 contains a minterm 0, minterm 2, and minterm 3. So 0 is basically X being 0, Y being 0, so X bar, Y bar. 2 means 1, 0. Binary representation of 2 is 1, 0, so that is XY bar, and 3 is 1, 1, so that is XY here. So that's a compact representation of a Boolean function here. Okay, a minterm is a product product term. Any min term is a product term that contains all the variables used in the function here. Okay, so that's the formal definition of a term here. So for example, if we have a 3-variable function here, so this is a min term, x bar, y bar, z bar here. Note that if you write a term as x bar, y bar, and it doesn't have a z in it, that's not called a min term. A min term must have all the variables that are there in that function here. Okay, so this is a 0 min term, 1, 2, 3, 100 is 4, and 101 is 5, and 111 is 7. So these are the various possible min terms that are there here. And we can write a function like this here. Suppose you're given a function which is sigma 147. It means that function takes a value 1 when these min terms are there here. So 1 we can write as x bar, y bar, z. That's 1, because 1 is nothing but 0, 0, 1 here. 4 is 1, 0, 0. So 1, 0, 0, 1 x goes here, 0, 0 becomes y bar, z bar here. 7 is 1, 1, 1, so x, y, z here. All right, so that's a sum of product kind of a representation. So we note that we have two kinds of complementary representation. One is a sum of product kind of a term where we focus on when does the function go to 1, when does it take a value equal to 1. And in the product of sum representation, we focus on when does the function take a value 0 here. So we focus on 0, so it goes to 0 here, so we write that particular term as x plus y bar here. So note that when x is 0 and y is 1, so when x is 0, this term is 0. When y is 1, this term is also 0. So 0 plus 0 is 0, and the function goes to 0 here. So that's why we write it in this particular form. When you see a 0, you write the term as it is. When you see a 1, well, you write the term with this complement. So now for this term also, function is 0 here. So when you see a 1 here, you write x bar. When you see a 0 here, you write it as it is, plus y. So we can verify that when x is 1 and y is 0, this particular term is 0 here, and function becomes 0 here. And so we connect it with a AND operation here. So when any of these terms is 0, function will go to 0 here. So that's an alternative representation of the function. You can concentrate on ones or you can concentrate on 0 here. So when we take this term like 0, 0 and we express it like x plus y, when we take 0, 1, 0 x plus y bar, 1, 0 will be x bar plus y. So each one of them we call it as a max term here. Okay. So this function here can be described by max term which is m1, this max term m1 dot AND operation m2, or we could represent it instead of a sigma operation, we could represent it by saying it's a product of 1 and 2 particular terms here. So that's an alternative representation of function f1. Okay, and for example, so what does f2 product of 0 and 3, what does that represent? Well, 0 is, note that 0 is x plus y, and 3 is 1, 1, so 1, 1 represents x bar plus y bar here. So with practice, what you can easily do is, given a representation like this, you can convert it into a Boolean expression of this particular form here. Okay, so for a 3-input function, these are the possible max terms that you see here. So you should become familiar with, if you're given 101, how do you write a max term? Well, again, this is 1, so we write x bar. This is 0, so we write it as it is. And this is 1 again, so we write it z bar. So it's the OR operation of all three. So what does a function product of 157? Well, 1 is over here, so we can write this out. Okay, so let's say we are given a function like this here, okay, a Boolean function like this. And we can see that this Boolean function, the truth table that we are given here, we can represent it in this particular form. It goes to 1 for this term 1 here, 0, 1, 1 is 3, 1, 0, 1 is 5, and 1, 1 is 7. So we represent it like this here. And we can write it out because it's 1 here, so 1 is 0, 0, 1, so 0, 0, 1 here, so only x3 is, the other ones are complement. And all 4 terms we can write it, and we can implement in this particular form. Fine, so given a truth table, well, this is the compact representation of the truth table. So sometimes the truth table it occupies a fair bit of area to show what the nature of the function is, and that can be written very simply by writing in this particular form here. So instead of writing a truth table, one can write this representation, which basically is this truth table representation here. So from this we get a Boolean expression. From Boolean expression we get a network of gates, and from here we can convert it into transistor circuit. Now what we are saying is that's not the full procedure for designing circuits, because from the truth table the Boolean expression that you get is not the optimized Boolean expression. In fact, we can show you that this expression can be simplified to simply equal to y equal to x3, which does not require any gate at all. Y equal to x3, which means you just take y and connect it to the input x3 directly. So such a complicated expression, and if you do not simplify it, then you would end up wasting so much of area, so much of effort in building it, while the actual expression in this case is an extreme case where y is simply equal to x3 here. So how do we simplify? So the point is, from a truth table you will get an expression, but this expression is not the simplest expression, it's not the optimized expression. You need to simplify it, and then you go ahead and implement it, because the whole goal of one of the goals of implementation is the circuit should be as simple as possible, so that the cost of the circuit is low. And when the circuit is simple, the circuit also becomes faster, because note that in this particular case, let's say y is actually equal to x3, so the signal travels from x3 to y without any delay. While here you can see that in the worst case, the signal, let's say, travels to y, it has to go through this NOT gate, so there'll be a delay. Every time it has to go through a piece of circuit, there's a delay. Then it has to go through this AND gate. Then it has to go through this OR gate. So when you don't have an optimized expression, what happens is the signal also encounters more delay here. So the circuit is more complicated. The path of the circuit from input to output becomes longer. So it encounters more delay also. So the circuit becomes slower also. So you end up losing not just in terms of the cost point of view that the circuit is more complex, but you end up incurring a performance penalty. And not only that, when you have more number of circuits, you can also think of each one of those pieces of circuits, they also dissipate power. So when you're switching some inputs, the capacitances have to be charged, discharged, and the switches are not ideal, they have resistance in them, and so power is dissipated. And so when you have a more complicated circuit, you have more power dissipated also. So it very rarely does it make sense. Sometimes you may want to add redundancy and deliberately make the circuit a little bit complex. Redundancy to make it more robust. I will not go into those details. But to save area to produce a cost-efficient circuit, to get a higher performance circuit, what you should do is you should optimize the Boolean expression, make it as simple as possible, and then implement it. Okay, so the goal of simplification is what? The goal of simplification is to reduce the complexity of circuit. Now this requires that we minimize the number of gates. We minimize number of gates, right? So the lesser the number of gates that you see here, the less complicated the circuit is. And note that each one of these gates, if we ignore this NOT gate for a moment, each one of these major gates that we have represents a term here. This particular AND gate is used to represent this term. This one is for this term here. So minimizing the complexity of circuit means minimizing the number of gates, which basically means minimizing the number of terms in the expression. The lesser the number of terms in the expression, the less complicated the expression is, the less complicated the circuit is. Not only that, the other one is, note that if you look at this circuit versus this circuit here. So we have a circuit given here, and let's say we simplify it to a circuit to an expression like this here. So if you compare the two circuits, the second circuit is simpler than this. We can obviously visually also see. But let's see, why is it simple? So one is obviously, if we look at the first level here, so this is the first level through which if we ignore the NOT gates for a moment, so this is the first level of gates that it goes through, and this is the second level. So with the first level of gates, if we look at it, we have 4 gates here and this has only 3 gates here. So obviously it's simple. But it is also, so overall this has 4 gates and this has 5 gates here. So this is simpler in terms of counting the number of gates. But the gates are also simpler. Note that here it requires a 2-input gate here, while here it's using all of them 3-input gates here. So note that a 2-input gate is considerably simpler than a 3-input gate. In fact, you can try and build a 3-input NAND gate yourself and build a 2-input NAND gate. And you will see that a 2-input NAND gate requires 2 N-type switches and 2 P-type switches or 4 transistors, while a 3-input NAND gate will require 6 transistors. So the more the number of the inputs to a gate, the more complex the gate is also. Okay, so what we are looking for when we are trying to simplify the circuit is not just that the number of gates should be smaller in number, and the number of gates corresponds to the number of terms that you see here, but each one of these terms should be as simple as possible here. So if you look at it, this term x1 bar dot x3 is a simpler term. It has only 2 literals, 2 input variables in it, and that's why it requires a simpler gate here. While this one has 3 literals or 3 inputs here, so it requires a more complicated gate here. All right, so this is what we are talking about. 2-input NAND gate is here and 3-input NAND gate is here. Right, so this requires 4 transistors, 2 P-type, 2 N-type. This requires 6 transistors, 3 N-type and 3 P-type here. Right, so the goal of simplification is minimize the number of product terms. As few product terms are there, well, the lesser the number of gates. And the other one is when you're looking at each one of those expressions, minimize the number of literals in each particular term. So each term also you should try to minimize the complexity, minimize the number of input variables that are there here. So these are the 2 goals. Minimize the number of terms, overall number of terms in the expression, and minimize the simplify the or minimize the number of literals in each particular term. So simplification for us, simplification of a Boolean expression basically means minimization. Minimum number of product terms, minimum number of variables in each. Variables is what we call as literals, minimum number of variables in each. So x1 is a literal, x2 is a literal, x3 is a literal. Okay, so minimum number of literals in each particular term here. So how do we minimize? Okay, so this is a Boolean expression. How do we minimize here? Well, we minimize by basic procedure for minimizing is, note that you're trying to reduce the number of terms, right? So how do you reduce the number of terms? You reduce the number of terms by combining 2 terms. So when you combine 2 terms, you get once. So when you combine 2 terms into one single term, so obviously you reduce the number of terms. Okay, so let's see. For example, x1, we can combine x1 bar x3 here. So x1 bar x3, so note that these 2 terms that you see here, you can see that there's something common between these 2 terms. x1 bar is common and x3 is also common. So we can take it out and then we get x2 plus x2 bar. So it's not just this thing here. So now when we take it out, what we get is x2 plus x2 bar, and x2 plus x2 bar is nothing but equal to 1. And similarly, if we take these 2 expressions and we can combine them, here also we get x2 per x2 bar here. And so the expression becomes x1 bar dot x3 and x1 dot x3. So this expression is much simpler than this expression. Now, how did we simplify? Well, we simplified by combining 2 terms together and we combine them in such a way that we look for this property here, that whatever is left, when you combine them, we are taking some factor out and we're leaving something in, and what we are leaving in is basically a function, a variable x and an x bar, so that it becomes 1, and therefore the term becomes simpler here. So note that 2 things have happened. When you combine these 2 terms here, you get one single term, which is x1 bar dot x3. So one single term, and the term is also simpler because it has only 2 literals. The earlier terms had 3 literals. Now the term is also simpler here. So you do one round of simplification. Now you can simplify this also, because we can take x3 common and then x1 bar plus x1, and that becomes x3 here. All right, so a complicated expression like this here is simply equal to y equal to x3 here. right? So that's the goal of minimization. Minimize the number of terms and minimize the complexity of each particular term here. Okay, and the main principle used in one of the key principles used in minimization is this one. That's x plus x bar equal to 1 here, and you can verify that if x is 0, then this term is 1, and so obviously the right hand side is 1. On the other hand, if x is 1, then this is 0 and this is 1 here. So x plus x bar equal to 1 here, right? So a very simple principle, and this is the principle that we are looking for. When we are combining terms, we are trying to see, can we use this particular property? So we are combining. So note that I would not combine x1 bar, x2 bar and x3 and first term and the last term, because when we combine them, you don't get inside the brackets something like x2 plus x2 bar, right? So you won't directly combine them. So it makes sense to combine first and the second term here, right? It doesn't make sense to, maybe you can combine, note that, first and third term also, right? Because in that x2 bar and x3 is common, you could take, and then you do that. Okay, so let's look at this one. How do we simplify this particular Boolean expression? So our goal is to use this principle and apply it here, and right? So we can see that, well, we can, first two term we can take x bar out, we can combine them directly, we can directly see here x bar, y bar plus y here, and then we are left with x, y bar here. So this becomes 1, and so x bar plus x, y bar here. All right, how do we now combine them? We cannot take any factor out. So by, when we're combining, we want to take certain factors out and leave certain things in the bracket. So we can't do that here. But note that we could also do the following here. The original expression that you see here, this expression has 3 terms. And what I've done here is, the first term is as it is, the second term. So what we have done is repeated the first term, x bar dot y bar, right? And then x bar y, and then x y bar. So all the second and the third term are here, second and the third term. The first term is here. And the first term has been repeated twice. Note that you can add any number of terms. You can take any term and you can repeat it as many times as you want. It doesn't alter the nature of the function. The nature of the function is we are looking for, when does the function become equal to 1? Well, the function will become 1 when this term is 1, when this term is 1. So 1 plus 1 is actually 1. So it doesn't really matter. So, but why are we doing it? Why are we taking a simpler expression and making it more complicated? So we are using the principle x plus x equal to x here. So which means that we can repeat a term and combine it with other terms as many times as we want here. So when we duplicate this particular term here, then what we can do is we can combine this particular term x bar y bar with x bar y here, and another copy of this particular term with this particular term here, and thereby obtain a simpler expression x bar plus y bar. And as compared to this particular part here. So use of this particular principle allows us to simplify the expression further here. So the point is, we are trying to simplify things by combining terms and taking out common terms and using this particular principle. And so when we combine one term with another, then if we don't use this particular principle, that term is gone. But potentially that particular term you could combine with some other term also. And so that's what we are saying. You could take a term and combine with any number of other terms also, if it helps in simplification here. All right, so these are the two principles that we use for simplification: x plus x bar equal to 1 and x plus x equal to x. So this is obvious, and this we are saying you can combine one term with another term as many times as it helps. Right, so we need this principle is fine. So, but to apply these two principles to a complicated expression like this, we have to really look at all this expression and hunt for those terms which can be combined together. And as the number of terms increases, it's not very easy to see which term can be combined with which other term. And so we need a systematic and a simpler method for applying these two principles. And one of the techniques for doing that is a Carnot map. It's a way of representing the information which is over here. The Boolean expression is a way of representing the same information in the form of in a visual form, which helps us to see where we can apply this particular principle and this particular principle. So let's stop here and we'll continue.